In this screencast, we're going to learn about solving differential equations or systems of differential equations, again using the existing tools. So we've already partially seen when we did integration that the scipy.integrate contains both routines for integration, which we've talked about, and solving systems of ordinary differential equations. In fact, there's not too much listed here, and the only thing that we're going to talk about is ODE-int. This is the general integration for ordinary differential equations, and will be sufficient for our purposes. There's more things that we could use with this ODE and complex ODE, but we're going to focus solely on ODE-int. Now, there's lots and lots of techniques for solving differential equations, and this has implemented actually a couple of them in a nice interface for us. When we look at this, it should remind us a lot of quad in that there's a ton of stuff here. Okay, this is a very powerful routine. Fortunately, we don't need to worry about most of the details of this. For our purposes, again, we can just look at the first few arguments, which look pretty familiar to us. Well, at least for the most part. There's a function that we pass in, there's some y0, there's some t, and there's arguments, optional arguments, which can get passed to our function. So if we look at what this says, this tells us, well, we can integrate a system of ordinary differential equations. It does this using a particular routine, LSODA, from this ODE pack. This is a standard, powerful routine, part again of a package of routines. And so we're just going to be using a particular interface to it. If we wanted to know more about everything that this could do and related functions, we could in fact just Google for this and find all kinds of information. Again, for our purposes, we just want to be able to solve a system of ordinary differential equations. So to do this, we need some function. This function, okay, is what goes in here, and it defines our system of differential equations. So dy dt is equal to this function. Okay, it solves what's known as stiff and non-stiff systems. Again, for us, that's details we're not going to worry about. So the important parameters are this function, okay, which computes the derivatives of y at t0. It calls it t0. What that means is that the current time step that we're trying to evaluate things at. We pass into ODE-int, okay, that function, y0. Y0 are the initial conditions. Remember, when we're solving differential equations, or at least when we're solving initial value problems, we specify initial conditions. For us, that's going to mean at time t equals 0. T, that we also pass in, is an array, as it calls it, a sequence of time points. These are basically the times at which we want to solve the system. The way we've discussed this in class is equally spaced time steps. It doesn't need to be equally spaced, but that's a convenience that we'll typically use. Okay, the initial value should be the first element of the sequence. So y0 should be evaluated, should be the conditions or the values of y at the first time in this array. And then, of course, args is an optional things that are passed to our function. Okay. There's other things that we can pass in. We can get full output that we've seen before, where this returns lots of information about what the calculation is doing. We can get some messages printed. Okay, again, we're going to ignore most of those. The important thing that this returns is, okay, well, it calls it y, but what this means is this is an array, okay, two-dimensional array that has one row for each time that we've passed in. That's what this means. And one column for each equation that we're solving in our system of equations. Okay, so this is going to return a two-dimensional array, assuming we have more than one equation that we're solving, that we'll look at soon. Again, if we get full output, then it returns a whole bunch of information, and it tells us about that here. And then there's a whole bunch of other options which we're not going to worry about, but you're free to look at. Okay, so for our purposes, we want to see how this works. So let's do that by considering a simple case of projectile motion. Now, before we do projectile motion, let's even do one step simpler. Let's just consider we drop a mass, okay, from some height, or really one-dimensional motion in a constant gravitational field. Okay. If we do that, we know from Newton's second law, we know what the force is. The equation of motion is just the net force is the mass times the acceleration. Or in other words, the acceleration is just, here written as the second derivative of y with respect to time, is just equal to minus g. Now this is a second order differential equation. ODE solves a system of first order differential equations, so we can easily turn this into such a system by breaking it up into pieces. So first derivative dy dt, let's call that something. Well, in physics we typically think of that as a velocity, so let's call that v. Okay. dv dt, which is the second derivative of y with respect to t, so that's just given by our equation of motion or constant acceleration, so dv dt is just minus g. So now we have two first order equations that we can solve, okay, we can use to plug into ODE-int. Okay. So that's great. But let's go one step further. Let's actually do projectile motion. Okay, well, projectile motion isn't that much more difficult. Now, of course, Newton's second law is a vector equation. We can look at the two components of that vector equation. The first one tells us that the acceleration in the x direction is 0. The acceleration in the y direction is what we just talked about. And so once again, we can split this up into a system of first order equations. The order we write these in doesn't matter very much, but I've chosen the following order. Okay, so again, dx dt is a velocity, so let's call that vx. dy dt is a velocity, let's call that vy. Okay, those are first order equations. dvx dt, well, that's the same as the second derivative of x with respect to time, so that's just 0. Okay, that's the acceleration. And dvy dt is also the acceleration in the y direction, so that's just minus g. So we have the system of four first order differential equations that we now need to solve. And so we want to write these in a format that we can use to feed into ODE-int. Okay, so let's do that. Okay, so I've already done that. Written this called projectile motion. Although I'm loading this locally, this is available from the examples page on the course website. And so here it is. We've defined some function. Maybe it's best to look at the documentation for this function. Okay, so this is a force on a projectile due only to gravity, i.e. it's implementing these equations of motion, written in a form that's going to be usable for ODE-int. So this function, you feed it y and t. That's what ODE-int wants. Y is an array specifying the current position and velocity of the projectile at some time, t. So t is also passed in. That's our current time step. What we're going to return is dy dt, okay, which is an array of the time derivatives. So in other words, this function should return the left-hand side of this, or the quantities that it returns are dx dt, dy dt, dvx dt, dvy dt. Okay? We know how to calculate these because we know how to calculate the right-hand side. Okay? Now, the order in which we specify these is entirely up to us. Okay? The algorithm doesn't care, ODE doesn't care. All it's doing is solving differential equations. It doesn't matter the order in which they're written. So we get to choose what order we write them in. Or to put it a different way, we have to choose what order we write them in and use that consistently throughout. So I've made a particular choice. I've chosen the order that I've written them in this little document. So in other words, y, there's four equations, so this has four components. First component is the x position, second component is the y position, then vx, then vy. Okay? That's important because dy dt will now be calculated in the same order, and it must be calculated in the same order, otherwise everything will get confused. So if we look back at the definition of the function we have here, okay, we pass in y and t, where y is this array. Okay, we want to return dy dt, which has the same size and ordering as y. So we can start by constructing that array. I like to use zeros like, since it does all the hard work for me. And then we just start filling in the entries. Okay? The first component of this is this equation, dx dt. And that's going to equal vx. What's vx? Well, vx is the y2, or the component with index 2 in this array, or at least how I've chosen it. So dvy dt of 0 is just dx dt, better known as vx, and that's vx. Similarly, for the next one, that's vy. Okay. The next component, or the next of dy dt, is dx dt. Whoops, or sorry, dvx dt. So the derivative of velocity with respect to time, and that's just 0. And similarly for the y component, and then we just return that. And so this is what this function needs to do. Okay. So if we look back at ODE_int, that's the function that we're going to pass in here. The other things we need to pass in are y0, which are our initial conditions, and t. So t is just some array that we choose. Here, let me arbitrarily pick a time between 0 and 2, do 1,000 steps. Okay, that's pretty arbitrary. We also need to specify y0. Now to specify the initial conditions, so we pick some initial position for x and y, and we pick some initial velocities. It's convenient to pick some magnitude for the velocity. So here, let's just choose 8 meters per second. And some initial angle. Okay. Here, let me arbitrarily choose 63 degrees. I convert it to radians because that's more useful when we want to actually calculate what y0 is. So y0 is 4 components, okay, because we have 4 equations, so 4 initial conditions. And again, these are in the same order that we specified when we defined the function. Okay. So the first component is x. I've chosen x at t equals 0 is 0. Next one is y. I've chosen that to be 1. And then vx, well, which is just v times cosine of the angle, and vy, v times the sine of the angle. Okay, so those are our initial conditions. So now we can use ODE_int to evolve our system of differential equations from these initial values up to the maximum time we specified in our array t, and it will evaluate it at each time step in this array. So let's go ahead and do that. Let's store the results in something cleverly called res. We feed it our function. Okay, we called that projectile force. We feed it the initial values, and we feed it the times. Okay. We run that, boom, okay, runs pretty quickly. A pretty easy system of equations to solve. So now if we look at this, this is in fact a two-dimensional array that contains each row, so this row, etc., is a different time step. Okay, so starting from t equals 0, going all the way up to t equals 2, filling in everyone in between. Each column is one of our coordinates, or one of the things that we're solving for. Again, this is in the same order that we specified them. So this is x, this is y, this is vx, this is vy. Okay. So again, this first row is at t equals 0, so that should agree with y0, and of course it does. Okay. We know that if we're in projectile motion, there's no force in the x direction, so the velocity in the y direction should not change. This is the velocity in the y direction. Notice that it remains constant. Okay. And so now we can do lots and lots of manipulations with this. For this purpose, it's useful to plot it. So let's plot x versus y because we know what that should look like. And the clever way to do that is using array slicing. So in the lab this week, we'll do a bit more with array slicing. But here we want a two-dimensional array, and I want to select all of the first column and all of the second column to plot against each other. How do I do that? Well, that's exactly what this does. Okay? Colon means all the values, so all the rows, comma, column index 0. Okay, so that's the first column here. Okay? If I want the next column, again, all the rows, so I put a colon, 1. If I plot this, lo and behold, I get, well, what should look familiar to us. Let's draw on the line y equals 0, and to be careful, we should actually label the axes, make it look nice. There we go. So this shows the trajectory of our particle shot from 0, 1 with the initial velocity we gave, goes up, comes down in this nice parabolic pattern. Okay. We could also look at the velocities. Would encourage you to play around with that yourself. That's great. Okay. Now, we can, of course, solve this problem analytically, but if we couldn't, we could now start manipulating this to try to get more information. For example, we see that this crosses 0 at some point. Okay? That tells me the distance that this projectile travels before it hits the ground. Where does that occur? In other words, what is this distance? So looking at the plot, we can get a rough estimate, or actually a reasonably good estimate, but I can stick my cursor there. And if I look down, I see x is equal to 5.713, and if I'm more careful, I can get it 5.76. So we see that we can get reasonably close just by looking at the graph. If I blew this up, did things like that, I could, graphically get a better answer. But we can do better than that. Okay? And this is where we can start pulling together some of the tools that we've used in the past to find where does this cross 0? Okay? So you should think about it, and there's a number of ways that we could think about doing that. Okay? As a first estimate, though, let's use something new, some very powerful function. Okay? What we want to know is where this crosses 0. What does that mean? Well, that means where y goes from being positive to negative. So if I knew where y became negative, that would get me at least close to this point. Well, not surprisingly, there's a function that does this for us, and shockingly, it's called where. Where is an extremely powerful function, and it's something that we will play with a little bit with it in this week's lab, and more in the future. Okay? And so we can look at the documentation, we give it some condition, and it's going to return to us some array in some certain form. In the most basic form, it's just going to return a list of index values at which the condition is true. Well, so let's just use it. Again, it's often best just to use this. So we want the y values. So again, the y values are the first column. So let's take all the y values, so all the rows in the y column, and we want to know where is this less than 0. Okay? So it returns an array. Okay, this is the index values in this array for where this is equal to 0. Notice less than 0. The first place where this occurs is at 791. So if I look at 791.1, okay, we see that yes, it is less than 0. If I look at one before that, it's not 0. So what that means is that this crossing of 0 occurs somewhere between index 790 and 791. Okay. We can see the time where occurs. So it's between this time, 1.581 seconds, and 1.583 seconds. Okay. We can see the x values where this occurs. Okay. Recall the x values were the first column, so we index 0. So it occurs between 5.744 and 5.751. Okay. So this gives us a rough estimate of where it is. In fact, we know that it's bracketed between these two regions. So if we think about this, there's now a number of things that we could do to try to improve this. One would be to just use linear interpolation. Look, I know that it's somewhere between these. I could use linear interpolation, or maybe I could use quadratic interpolation, use a few more points, or maybe I could use a spline. Okay. If I construct a spline, okay, y is a function of x, I could then use a root finder to find where does that function equal 0. That's a perfectly good approach. Another approach is to say, well, what I'm really interested in is I'm really interested in x as a function of y, and I want to know the value of x when y is equal to 0. So I could invert the function using interpolation, and that could be done very nicely with, for example, a spline. So let's import scipy.integrate as we typically do, and remind ourselves that we can construct a spline, but recall we have this big problem that if we're going to invert this, what we want is we want x as a function of y, so we want to switch what we typically think of as x and y. Okay? And the x thing, in this case, the values that we're going to evaluate our spline at, must be increasing. Well, clearly this y is not always increasing. It starts increasing, which is great, but then it starts decreasing. Now, if it were just decreasing, we would be happy because we know how to reverse a spline. Or sorry, we know how to use array slicing to reverse the order of an array so that we can then feed it into a spline. But this has the unfortunate behavior that it's increasing and then decreasing. Okay, so what do we do? Well, we're only interested in what's going on up here, and so we could just restrict ourselves to be up there. Okay? We already know that this is around index 790, and so in fact we could use that information to just use a few points around here. And that would be a perfectly good thing to do. You should think about how you would do that. Instead, though, let's be a little more generic. Now, as we said, if this were when y is just decreasing, we're perfectly happy. We know how to reverse the order of that array, and so we could happily go ahead and construct a spline with that. The problem is that we're increasing up to a maximum and then decreasing again. So really, if I knew where this maximum occurred, or if you like, I knew where this started decreasing, I would be in great shape, and I could just start, using values from here in my spline. Ignore all this because it doesn't matter anyway for finding this value. So what we would really like to do is find this maximum. Well, how do we find a maximum? Our first thought might be to take a derivative and set it equal to 0, which is absolutely true. But recall that in our array, we've essentially already done that. We've solved for x, y, vx, and vy. So in fact, we know at the maximum occurs when vy goes from being positive to going negative. And so in fact, we can use our same trick that we did here. Instead of asking where y goes negative, we could ask where vy goes negative. Okay, there's a lot more values. We see that the first one occurs at 364. So at index 364, we see that the velocity is negative, vy is negative. Okay? And y has some large value near the maximum. Okay? You should explore more in this array to verify that this is in fact a maximum. Okay? And so what we're interested in using then are just the y values from 364 to the end. Okay, so from somewhere around here to the end. Well, we know how to do that with array slicing. This means start at 364 and go to the end. Great. Lots of values, and again, they have the unfortunate behavior that they're decreasing. Okay? So what we want to do is reverse the order of this array. Well, we know how to do that. We can step backwards in the array. So our first guess might be to do something like this. Okay? Well, we don't have to just guess, we can do it. Notice if we do it, this is not what we wanted. Okay? Notice that this goes from 359 to 1, and there's fewer values. In other words, it's starting here and walking backwards. Well, because that's exactly what we told it to do. We told it to start at 364, go to the end, whatever the end means, stepping backwards. Okay? So that started here and went backwards. What we really want to do is we really want to start at the end and walk to this point. Okay? So in other words, what we really want to do is something like this. So start at the beginning, whatever the beginning means, okay, and walk backwards until we get to 364. So starting at the beginning means, we're starting right off the edge here, and if we're walking backwards, then the first point we walk to is here, and then continue walking along until we get to 364, which will be near the maximum. So if we do that, we see that yes, this does have the right behavior. Okay, it goes down to, or it starts at a value down here around -4, and walks all the way up to the maximum. Okay, so this value. So that's great because now we can construct our spline. So we'll call it xy because it's x as a function of y, interpolated univariate spline. We reverse the order of y, And we need to do exactly the same thing for x. Okay, so this will use the correct x values. So if we do that, we can now calculate x of y at 0, and this should be the range. Okay, this will be the value where this crosses 0, at least according to the spline. We can verify that that's correct because we saw again that the answer should be between these two index values, and so this value should fall between these two values. And notice that in fact it does. This is slightly larger than this. Okay, so this value happens to be close to this point, which is great. Okay. So that gives us one example of how we can use this. Okay. Using where, using array slicing, we can do pretty incredible things very easily, particularly once we start coupling this, with all the things we've done before, root finding, splines. Okay? We really can build up very powerful things, do very powerful calculations very simply. Okay? So this shows us one example of doing that. We will see more in class, in the homework, in the lab. We're going to continue to build with these tools as we go along.